the length of a circular arc is in direct proportion to the angle that it subtends. In this section, we'll study the relationship between our angles and radians and the length of a given circular arc. To do this first, let's recall the definition of a radian measure, and then also let's go ahead and draw what this means. First, we start off with a circle of radius 1. Here's our circle of radius 1. Then we have a point in the center of the circle, which is the vertex of an angle. And the measure of this angle in radians is then the length of the arc that subtends this angle. And this picture is given by this blue arc here. If we remove the restriction that this circle has to have radius 1, then we get the following relationship between radius, angle, and length of the arc. That the length of the arc given by S that subtends an angle of theta has the following property. What this means is, again, given our radius and given our angle theta, we can find what our arc length is, and vice versa. Given any two pieces of information here, we can find the third. Another nice feature of this relationship is that this formula allows us to find radians given a circle of any radius. Let's try a problem out. Example number 4. A central angle theta in a circle of radius 4 is subtended by an arc of length 6. Find the measure of theta in radians. Before we solve this problem, let me note that the previous relation, S is equal to R theta, is only true when theta is given in radians. This is an important fact. If theta was given in degrees, this relationship is not true. Let's go ahead and draw a picture for this problem. First, we have our circle, which is given by a radius of 4. Then we have an arc length, which is of length 6. And we're looking for theta. We can fill in for unknowns and then solve for theta. In this case, we know S is equal to 6, R is equal to 4, and theta is our unknown, which gives us that theta is equal to 6 divided by 4, which is 3 divided by 2. And this measure is given in radians.